Hey everyone, I just wanted to do this video on ice tables for our class because it it's kind of a very new concept and it takes a lot of time to digest. So in video format, you're able to really pause and sort of take a moment to try to take inventory of what's happening. Ice tables are going to be used essentially when we're not at equilibrium. So that's going to be the idea for this. So what happens if a system is not at equilibrium? First thing is that we said that the Chatelier's principle states the reaction will react in one direction until it reaches equilibrium. And then if you only have the reactant side, the reaction will make products. And if you are starting with all product, the reaction will make reactants. If you start with a mixture of product or reactant, you have to figure out which way the reaction will shift. We don't have to worry about that. So we are just focusing on the shift if we have all reactants or all products, essentially. So set up the ice table to find those concentrations. So that's going to be what this video is on, is setting up that table. Okay, so this question says the equilibrium constant K for the following reaction is 5.64 times 10 to the negative 5. So that's actually no different. That's just our constant value. We've seen that before, and they actually have that for us already. And it says initially H2 has a pressure of 0.67 atm, I2 has a pressure of 3 atm. At equilibrium, what will the pressure be of HI? So first thing we have to do is write the equilibrium expression, write the K expression. So if we think about what that means for this reaction, and this notation looks a little funky, but all that this literally means is that it's products over reactants, like we said, right? And it's the pressure of HI. We're talking about pressures here in ATM, right? The pressure of HI squared, that's all that this is saying, and we squared it because there was a 2 coefficient in front, if you remember, over the pressure of the reactants, so the pressure of H2 times the pressure of I2, and there's no coefficient number in front of these in this balanced equation, so there's no exponent for those values. We just pretty much use them as is, and that's our expression, and they gave us what that actually equals, which is 5.64 times 10 to the negative 5. So we have that all set up, essentially. Okay, so that's for how we start off. Then we set up our ice table, because again, we're not yet at equilibrium. If we were at equilibrium, we could just take these values and plug them in directly. But this is saying initially. This is not saying at equilibrium. And this expression is only meant for when we're actually at equilibrium. So we need to figure out what it would look like at equilibrium. So, ice table, the I in ice stands for initial, the C stands for change, and the E stands for at equilibrium. So we just take our initial values and plug those in beneath our balanced equation. So H2 started off with 0.67 atm, I2 started off with 3 atm, and we didn't have any information about products, so we're assuming we had no products. So 0 atm of products. So this is initially. This is before anything has even had a chance to react yet, because we know that once things start to react, we can expect a shift toward, in this case, products, right? So this is we mentioned a moment ago how if we have all reactants, we can expect a shift at least to products to some extent. And if we have all product, we can expect a shift to reactant, and that's a different kind of problem. So for this particular problem, we just put in our initial values, just like they're in the problem. Our change is what change we can expect as things shift toward equilibrium. And we don't know exactly what that will be. So we actually, anytime you don't know what a value is going to be, use a variable, right? So this is what our change will look like for this problem. So let's look at one thing at a time. H2, that's a minus X. It's a minus because we are starting with all reactants. So we know that those are actually, we're going to lose some of it. We're going to lose some of the pressure from the reactants because we know those are going to shift over to products. Like that's a guarantee as things start to move toward equilibrium. To what extent, we don't know, but we know the shift will happen. I2, same thing. It's a minus because we expect to lose it because in this problem we have all reactants and no products. So we know we're going to have some loss of reactants toward products. It's going to shift that way. The reason why we just use X is because of, again, our coefficients. So in this balanced reaction, we would expect to lose 1x and 1I2 essentially overall is how much we'd expect to lose. And then for our products in this case, because we start off with no products, they stand to gain from this. They are definitely going to gain, and we put a plus there because of that. We put plus 2x because it's twice the, because of our balanced equation, we've got that our 2 as our coefficient, and the plus because they're gaining. So that's what we can see for the change there. But again, this row is specifically based on coefficients and who's losing, who's gaining, essentially. So that's our change. Our equilibrium value is going to be pretty much if you combine those things. So first of all, you want to really think of this thing as being a definite number. These are expressions that mean some number. We just don't know what that number is overall, but that's what these expressions mean. And to get there, it was pretty much just going down and doing the operation. So in this case, it was 0.67 minus x. That's literally what we have here. 3.0 minus x. That's what we put here. And 0 plus 2x. This last row is, again, these actually stand for numbers, is what we expect to actually happen in an at equilibrium. So this is our equilibrium values, essentially. Because we figured out to some extent, our equilibrium values, these are actually allowed to be plugged into the equation. Remember before we said we can't just plug in the numbers that they gave us because this problem specifically says initially. And our equilibrium equation can only be used if we're actually at equilibrium. So at this point now we actually have values for that. So this is where it starts to take another funky turn. So we literally take these values and plug them into our equation as is. So these are our values. Substitute them in. Here's our initial equation we set up, right? We squaring hi, and then it's just h2 times I2, pretty much. Okay, so we plug that in. Remember it was hi squared, so we found that at equilibrium, hi will equal 2x because of our 0 plus 2x, so it'll just be 2x. So we put that in as 2x, and this is where people tend to make the mistake. It's 2x the whole quantity squared. 2x is the equilibrium amount of pressure we expect for hi. And so we're not just squaring x here. 2x is actually some number of pressure we're expecting. So we need to square that whole number. So that means we're squaring the 2 and the x. So be very careful there. Don't just put 2 and then x squared. It's the 2x, the whole quantity squared is pretty major. Or if it was 3 or whatever coefficient, it really depends. But we need to make sure we did it for the whole thing. Okay, and then for our pressure of H2, we literally just plug in this, what we found. So 0.67 minus x, that goes in there. And 3.0 minus x, that goes in there. So we literally just move them over. But it's really important that you write this out first. Like, there's a million ways to make a mistake in these problems, and it's going to happen if you didn't first write this part out initially. Write the generic equation out for this particular problem. Okay, so that's what we're looking at. Now at this point, remember we said that that is equal to some value, right? It's actually equal to this number. So at this point, if you wanted to, you could actually figure out what x is. That's our goal right now, is to figure out what x is. And you could do it, but it would require pretty much use of their quadratic equation, because you're going to end up with an expression of something x squared plus something x equals a constant when you actually like mess around and solve all of this. And pretty much you would, when you get your answers, you would take the positive answer that you got for x, and that would be your number. But we're not going to do that. We don't have to do that. So instead, we're going to make this assumption that'll be key assumption that you can make for all of your problems at this level. That assumption is that because this value is so small, we're going to go ahead and assume that this x value is also relatively very, very small. In fact, anytime you have a very, very small number for a variable, right? And if you're taking that number and adding it and subtracting it relative to a whole number, we know that adding or subtracting a very small number will not have very much impact on the number, right? Like 0.67 plus 0.001 won't be much of a difference, or I should say minus 0.001 won't make much of a difference. 3.0 minus 0.001 won't make too much of a difference, right? So we're going to make an assumption that shouldn't really affect our answer too much. And we're literally just going to assume that these two x values on bottom, because they're being subtracted, we're going to assume that that is such a minimal change that we can actually remove them. Now, we can't just eliminate the x on top, because that's being multiplied by 2n squared, right? So that's actually a big difference if you're multiplying or squaring or dividing. a number, even if it's small, it makes a large impact. So that numerator, we can't make this assumption for. But for the bottom, we can go ahead and eliminate the x's there because we're subtracting those, and that's a relatively small number. So our new expression really becomes this. 2x, the quantity squared, over 0.67 times 3. So all that I did here was I removed the x's from the bottom. And now we have like a wavy equals because it means like just about is what it means. It no longer means exactly because we messed with the numbers a little bit here. But it should still work very, very close enough to what we need to our actual answer. Okay, so hopefully you're following along so far with what occurred. Again, pause if something's not making sense. But at this point, this is our expression. Now we're in a position, right? This is actually a lot more neat and tidy where we can actually solve for x this way. And that's our goal, is to solve for x. So this is our setup. We're trying to solve for x at this point. Now just remember, first of all, of course, we would multiply both sides by 0.67 times 3, right, start to work our way toward x. And then notice as well that we did 2x the quantity squared, so this became 4x squared, not just 2x squared. The 2 got squared as well, so that's a mistake most people will make. Be careful. And then when we solve for x, right, by dividing both sides by 4 and by taking the square root, we get this value. This is our value that we get. Okay. So, and our last thing is we have to be careful. The problem said, what is the equilibrium pressure for HI? Now remember that each of these things at the bottom actually stands for a number. Each of these values, each of these expressions at the bottom stands for a number that is the pressure at equilibrium of those gases. So this is the pressure of H2. So if we were to actually, if we want to find the real pressure of H2 at equilibrium, the real answer is 0.67 minus our x value, which is a number, right? So that's our actual pressure. And our real answer for the equilibrium pressure of iodine, I2, is 3.0 minus this number. That's our equilibrium pressure. So finally, to actually answer the problem, it wasn't just enough to find x, because x is just x. Our actual equilibrium value for the pressure of HI is 2 times x, is what we figured out. So 2 times x actually comes out to 0.011 atm, and that's the actual answer. So, like I said, it takes some time to digest. If you're really thoughtful in what you're doing and slow down, it should work a lot better. And if you first write out that expression every time. Again, keep those web assigned help requests coming. Happy to help. Let me know whatever you need.